Hello, my name is Chris Eberly and I'm an applications engineer at PLECS. I'd like to welcome you to this tutorial video on scripting using PLECS Standalone. Running simulations from a script allows you to examine the effect of varying parameters or to post-process the simulation results to extract relevant information. Since PLECS Standalone does not have a link to the scripting interface of MATLAB, alternative scripting methods have been implemented. PLECS Standalone offers an internal scripting feature as well as the ability to access and control a PLECS simulation from an external programmed script. This tutorial video will demonstrate how both of these scripting methods in PLECS Standalone work. The first method uses scripts that can be executed directly in PLECS Standalone. These scripts use a syntax which is very similar to that of MATLAB. We will use the boost converter demo model that is provided in PLECS and add a script to it to vary parameters and compare the results. From the simulation menu of the schematic editor, select Simulation Scripts to open the dialog. The left-hand side of the dialog window shows a list of the scripts that are currently configured for the model. To add a new script, click the button marked plus below the list. To remove the currently selected script, click on the button marked minus. You can reorder the scripts by clicking and dragging an entry up and down the list. The right-hand side of the dialog window shows the script in an editor window. We want to create a new script that will run several simulations with a varied load resistance. Each script must have a unique description, so we first provide a name that's relevant. A couple more things are important to understand to execute a script properly. PLECS Standalone uses the Octave language to execute simulation scripts. A full syntax description of the Octave scripting language is available in the Octave documentation on the web, but generally you are safe using MATLAB commands. In addition to generic Octave commands, you can use a set of PLECS-specific commands to control PLECS from within a simulation script. The full list of these commands are provided in the PLECS documentation, but we will highlight some of them here. A function called PLECS has been added with a set of predefined commands for tasks such as changing parameters and running simulations and analyses. We will start our script by reading a component parameter, which can be done with the PLECS get command. The PLECS get command requires a component path and a specific parameter name as arguments. We want to create a variable for the name of the circuit. To do this, we will use the special parameter current circuit, which can be used to query the name of the model that contains the script currently being executed. This is a special command in PLECS Standalone that is useful for constructing a component path that does not depend on the model name and can therefore be reused for multiple scripts. Note that the component path has to be an empty string for this particular command. In the same fashion, we can return the value of a parameter using the get function or set the value of a parameter using the set function, but we won't use these commands now. In order to handle the traces and scopes in the model, we also need to create a variable for any scopes we plan to look at. Since our model only contains one scope named scope, then we can do this step in a single line. We create this variable as we need to refer to the scope later in our script. These first two lines of code constructed a path to the component scope. Next, we want to create a structure array for the load resistance. There are three option structures predefined for overriding parameters defined in the model. Using the structures enables you to run simulations for different scenarios without having to modify the model file. The model var structure variable allows you to override variable values defined by the model initialization commands. The solver op structure variable allows you to override the solver settings specified in the simulation parameters dialog. And the analysis op structure variable allows you to override the analysis settings defined in the analysis tools dialog. In our script, we want to vary the load resistance value and display the simulation trace for each one in the scope. Therefore, we will need to use the model var structure to be able to overwrite the resistance parameter for each new simulation run. The resistance will require its own structure. Let's first define a load structure with one field containing a variable var for the resistance value in the model. We will also initialize var to 4 ohms, which is its assigned value currently in the model. This value will be used in any parameter expression that references this variable. Of course, we can't forget to also change the resistance value parameter in the model from 4 ohms to this same variable var r. We now need to embed our load structure into the model var structure that I previously mentioned. We will define this as var structure and embed the load structure inside it like so. Just to recap, we now have a nested structure, which we can use to vary the load resistance. We can use this method to vary any other parameter in the model we wanted to, for that matter, by simply creating a new nested variable. As a good practice, I will now add a line of code so that any traces in the scope are cleared at the start of the simulation. This might not matter for the first time the script is run, but can be useful when running many iterations. The PLECS scope command will allow us to clear the traces, which I am now providing. Note that the second parameter of the function is the path of the scope, but since we already saved this as a variable, we can just reference it. In addition to clear traces, hold traces and save traces are predefined arguments that will do the action that their name implies. Now we can create an array of resistance values to sweep through. We will step the resistance from 3 to 4 to 5 ohms. Using a loop is the most efficient means of coding a routine to run multiple simulation traces. We will use a for loop whose index counts from 1 to the length of the resistance array, which in this case is 3. Now we assign the indexed resistance value of our array to the structure variable, while remembering to use the nested structure notation. The PLECS simulate command starts a simulation, and we will want to pass our nested structure as an argument to override the resistance value in the model during each simulation run. We can then hold each trace using the PLECS scope command. When using the hold trace argument, we can also assign names to each trace. The octave matrix to string function will print the resistance value of the particular run into the trace name, so that the first name will be R equals 3 ohms, for example. Finally, we close the for loop with an end statement. Let's just discuss once again what this block of code does. Inside of the for loop, each value of R vals is assigned successively to the structure member variable var r. A new simulation is started, and the resulting trace is held in the scope and given a specific name related to the corresponding resistance value. We can then click Accept followed by Run, and we see that this will automatically perform 3 simulation runs, each with a unique value of resistance, and the resulting traces are overlaid on top of one another. This script can be extended to include more resistance values, or alternatively to obtain simulation results for varying multiple parameters in the model. A demo model is included in PLECS that also shows how some additional post-processing can be defined. Now that we are comfortable on the internal scripting method of PLECS standalone, we may want to use an external scripting language to do the same type of tasks. PLECS standalone offers an XML RPC interface that allows any other program that can send XML RPC requests to control PLECS. PLECS acts as an XML RPC server which processes requests from the XML RPC client. XML RPC is a lightweight protocol that is supported by numerous scripting languages. Python and Ruby support it out of the box, for example, but other scripting language extensions for XML RPC support are available for free on the internet. For the following demonstration, Python will be used. It should be mentioned that while Python-specific syntax and commands are shown here, the same functionality could be implemented in another language with ease. I'm going to open an existing script from the Python idle shell. The script contains the same commands in Python code as I just showed using an internal simulation script in PLECS standalone. The first step is to make sure that the XML RPC interface is enabled in the PLECS preferences and that the port matches the one configured in the script. In this case, we are using the default port number of 1080. By executing this Python script, we can see the same results as we had before using an internal PLECS simulation script. This concludes our tutorial video on scripting in PLECS standalone. All of this information and more specific details can be found in the PLECS documentation that is accessed from the Help menu or in the PLECS user manual available from our website. Those that are interested in scripting in PLECS standalone are encouraged to read through this information. Thanks for watching.